This is the argmin channel on real analysis, lecture 6, monotone convergence theorem, its applications. So we actually looked at the monotone convergence theorem at the end of the last lecture and proved it there. So if you're looking for that, go look at that video. I kind of screwed up with the ordering of things. But anyways, let's just to recap, it says that every monotone increasing sequence that is bounded above converges, and every monotone decreasing sequence that is bounded below converges. We just proved it, but we didn't actually look at why this is something useful. So it's useful for when you want to show that a recursively defined sequence converges and to find that limit. And it's also useful for something you'll see later called the nested intervals lemma. So uses 1, showing convergence of recursively defined sequences. So write down what I said. 2, proving the nested intervals lemma. All right, so let's look at that first application and see how we use the monotone convergence theorem. So if you don't remember what a recursively defined sequence is, here's an example of one. A1 equals 1, and an plus 1 is equal to the square root of 2 plus an. So the next term depends on the previous term, so it's defined recursively. So we have here that an plus 1 is determined by an. And what we want to do is prove the sequence converges and find its limit. And since this is the monotone convergence theorem video, of course we're going to be using that. So to do it, we're going to show an is monotone, either increasing or decreasing, and bounded either if it's increasing above, if it's decreasing below. This example is constructed to be nice, so I'll just say that it's monotone, but to find out which monotone type it is, we can just find the next number in the sequence. So a2 is equal to 2 plus a1 is equal to square root of 2 plus 1 is equal to square root of 3. So that's about equal to about 1.7, I believe. So that's greater than 1. So let's assume it's monotone increasing because the second term is larger than the first term. And we're going to be using induction over here. This, as is the case usually when you have something to do with recursions. So a of k plus 1 is greater than or equal to a of k. So a k plus 1, if we just put that into the definition, is equal to square root of 2 plus a of k, and that itself is less than or equal to 2 plus ak plus 1. And how we go from there, just some side work, is ak plus 1 is less than or equal, sorry, ak is less than or equal to ak plus 1. Add 2 to both sides. And then take the square root. So that's how we got this line, if that wasn't clear. And substituting in to that, we now have, this is exactly the definition for ak plus 2. So we can conclude that it's monotone increasing. Now we show it is bounded. Suppose A of k is less than or equal to some number. We'll fill it in later. Just so we're clear, we want to show that it's bounded above, not, we don't care if it's bounded below to apply the monotone convergence theorem. So suppose that is true for all k in the sequence, or yeah, then if we define things, ak plus 1, we know that is equal to square root of 2 plus ak. And to make things nice, we can say that that is less than or equal to 2 plus 2. So put that in there. So ak is less than or equal to 2. So that's how we get that inequality. And that just gives us a nice little bound. So ak is less than or equal to 2, and ak plus 1 is less than or equal to 2. So we can say ak bounded above by 2. So because it's monotone increasing and it's bounded above, we can now say that ak converges. Okay, now let's find the limit. We know that a of n goes to L, and so we see a definition again. A n plus 1 is equal to the square root of 2 plus a n. So as it grows bigger, that a n plus 1 becomes L, and that a n becomes L. And squaring both sides, we get that. And then rearranging, minus 2 equals 0, so L minus 2, L plus 1 is equal to 0. So L equals 2, or L equals -1. So we have two options for L, but since we know that every element in the sequence is positive or non-negative, the limit must be non-negative as well. So let's write that down. Since a n greater than or equal to 0 for all n in n, L is greater than or equal to 0 as well. Therefore, L equals 2, since L equals -1 is negative, and we found the limit. And that concludes the example. Done. Now, as another application of the monotone convergence theorem, let's look at something called the nested intervals lemma. Its statement is that if you have a closed interval and a chain of supersets, then the infinite intersection of them is non-empty. So if In is a closed interval for n in the natural numbers, then if each one is a superset of the next one, and so forth, all the way up to infinity, the infinite intersection of these sets is non-empty, not equal to the empty set. So to prove this, we're going to define the intervals by their endpoints. First, draw out the nested intervals and relate the nth and n+1 terms with an inequality. And finally, find some monotone structure and apply the monotone convergence theorem. So, proof. Let's make the INs nicer by writing them out explicitly. So it's a closed interval, so we can write it as AN BN, where AN is less than or equal to BN for each n in n. Then if those intervals are supersets of each other, they will look like this. So you have A1, A2, so forth, all the way up to N, and so forth, Bn, B2, B1. So we have that I1 is a superset of I2, is a superset of everything in here in a nested way. So for all n and n, we have that A of n is less than or equal to an+1, and that's less than or equal to bn+1 because the way the closed interval is defined, and that is less than or equal to bn. From that, we can get that an is less than or equal to bn, which is by definition less than or equal to bn-1 because of how the nesting works and the supersets, and so on all the way up to b1. So an less than or equal to b1, and by similar logic, bn is greater than or equal to a1. So we have that since an is less than or equal to an+1, an is monotone increasing, and bn is greater than or equal to bn+1, so bn is monotone decreasing. And from these inequalities, we can show that they're bounded. So an is less than or equal to b1 for all n in n. So an is bounded above, and bn is bounded below by a1 for all n and n. So let's forgot those. Bn is bounded below. So finally here we can conclude that an converges and bn converges. Let's write in the parentheses so we're clear that that is the sequence. So now just so we're not lost, we want to show that this finite intersection is non-empty, or infinite intersection, sorry. We have that an, let's suppose it goes to L, and bn goes to m, where from before, L is equal to the supremum of an, excuse me, and m is equal to the supremum of bn. Since we have that an is less than or equal to bn for all n in the natural numbers, we have L is less than or equal to m, and that's just from an application of the Squeeze theorem. So for all n in n, we can say that an is less than or equal to L, which we know from that what we just showed is less than or equal to m. And since that's the lower bound of b, whoops, that's supposed to be an inf there, is less than or equal, less than or equal to every bn. So by the Squeeze theorem, we have L and M between two sequences A and Bn. So the sequence L, L, L is squeezed by A and Bn, so is the sequence M, M, M. So we must have that these are both in that intersection. So they can't be empty. And that's it. As a preview of where we're going, let's first define subsequences. So a subsequence of an going from n equals 1 to infinity is another sequence a n k, such that from k equals 1 to infinity, such that n1 less than or equal to n2 less than or equal to everything following that. So some examples of subsequences. Say we had some sequence A1, A2, and so on. If the nk is defined to be equal to the power of to, let's say, 2k, then that subsequence would look like a 2 times 1 is 2, 2 times 2 is 4, a 6, and so on. And if nk were defined as k squared, that would look like a1, a4, a9, and so on. So what we need here is that each one is less than the next one. So 2 must be less than 4, must be less than 6. So an example of what isn't a subsequence, let's just say a3, a1, a7 isn't a subsequence because n1 equals 3 is not less than or equal to n2 equals 1. Not a subsequence. Okay, and I'm going to introduce this theorem, the Bolzano-Weierstrass theorem, which talks about when subsequences converge. Bolzano-Weierstrass. It's stated as every bounded sequence of real numbers has a convergent subsequence. We're not going to prove it in this lecture, but as an example of what that means, take for instance this sequence which we showed diverges. We have a convergent subsequence if we take nk equals 2k, so every even element, so that subsequence would look like just, so k, n here is even, so -1 to the nk is even, so that was just 1. Just do that. So that subsequence then is ank is equal to 1, 1, 1, which converges to 1. And as another convergent subsequence, you can have another one. It doesn't have to be unique. So let's separate those. Ank here. This will be the odd one, so those are -1, and that goes to -1. And that's it for this lecture.